All right. Can everyone see that?
You see it fine.
All right. So I'm going to talk about a topic that I primarily did this one because I've found myself sort of philosophically struggling to figure out how to relate a concept that I run into at work with sort of bigger software systems and how it might connect forth. So what I'm going to so this presentation was partially me sort of working through how to relate an idea to another idea. So in any event, so I'm going to cover what is dependency injection. It may be an unfamiliar term to folks in the fourth community. It's one that has a lot of prominence in some others, and also sort of why you might do this dependency injection thing. It's going to turn out that because it's an object-oriented concept, I will show off yet another object-oriented system in fourth. Unfortunately, I'm going to add to the n+1 problem there, and then I'll talk about a tool I made for dependency injection, and then ask the question: does it really have to be this complicated? So here we go. So. Dependency injection is a sort of term of art that's very popular in the Java community and other Kotlin and C# communities. It refers to the idea of inversion of control, that you might want to, instead of reaching out and depending on a set of things, instead have those things passed into you. The phrase that gets used is the Hollywood principle: don't call us, we'll call you. And so the idea is that you receive your dependencies rather than make them solid dependencies. And this means that where normally you might think of like a black box where you very carefully specified the outside of the box, but maybe that box contains other boxes inside. With dependency injection, you try to not only specify the interface sort of for the exterior, but sort of the interior, the other components that you need to plug into. But this has also been called kind of a $25 term for a 5-cent concept, because there really is, in one sense, not a lot to it, but especially in the Java community, there's a lot of stuff built up around it. So where is it used? As I said, Java, Kotlin, C#. It's not as popular in languages like C++, or Python, and certainly I've never seen it in the context of Forth. It's probably popular in these languages because they're strongly typed. They have the property that it's a little bit challenging in them to dangle things sort of out globally. It's sort of a discouraged pattern, and even things at module scope are tricky. The one challenge is, I think, that causes it in these languages to be popular is that creating little functions or closures is hard, both in the literal typing sense, like there's a lot of boilerplate in these languages, and so the minimum sort of unit of code that you can produce is fairly large, but also in the sense that because you have to specify all of the data types very precisely, that also makes it challenging to produce small little fragments of stuff. And I think it's also just because these languages don't have a lot of dynamism to them, and you can't monkey patch things. So I'm going to show this in Java. This is a little weird for this forum, but I think it helps to start here. So the idea would be, suppose that you have some class foo, and it depends on two other objects of a class bar and baz. This is a direct dependency. You just call new to create them, and the challenge is, well, what if you wanted to swap these out? And the prescription with dependency injection is that you would change your constructor so that you pass them in. You receive bar and baz, and then way up top somewhere, when you're instantiating foo, that's where you go and create a new bar and a new baz. And it's a seemingly simple transformation, but there's a lot that has been done to sort of make that more ergonomic in the Java community. So why would you do this? Well, one reason is that it makes it easier to test things. If you've got a test version of bar or something, you can have you can pass that in instead when you're building a test version of it, and that can be great if imagine and certainly in the kinds of programs where this is relevant, you've got large systems where objects might represent whole servers or services, and large or a database or something like that. And so being able to swap in a mock or a fake database becomes useful. It can make it easier to refactor if you've sort of plugged everything together up top. Changing how things are glued together can be made easier this way. And particularly if you want to swap in alternate variants of things, either statically or dynamically. And then the one that I think really makes this sort of take life is that there are a bunch of frameworks that are sort of driven by this and make it even easier. And it lets you do things like sort of have powerful additional objects that you kind of sprinkle into your program, and they find their way through the dependency chain of the program. And can kind of do global things that you can kind of reason about in a more sort of rarefied way from the program. You maybe drop in a different logging system, and then the entire program sort of responds to that. And it encourages encapsulation. It forces you to think not only what is the API contract of your inputs, so to speak, but also of the things that you rely on. And it leads to a kind of Lego block programming style where you're gluing things together. And I think that's another part of this in the Java community. You have a lot of code reuse of really, really large pieces of code. And so being able to sort of have a pattern for how to glue them together is useful. Let me talk about an example that gets used with one of these frameworks. It's the coffee maker example, and that might help motivate this a little as well. So the idea is that you have some coffee maker, and in a very abstract sense, it depends on it needs a pump to pump the coffee through. It needs a heater to heat the coffee. And then, like all good pieces of electronics, it will keep a data log of what it's been doing. And then for this particular instance of a coffee maker, we're going to use a pump type called a thermosiphon, where it uses a heat differential to pump. And so then it in turn needs a heat source, and it needs to be able to log. And then let's suppose that we're going to use an electric heater as the heat source. And each of these, you'll notice, needs to be able to log. And so if you glue these all together, the coffee maker's need for a pump can be provided by the thermosiphon, its need for a heater by the electric heater, and these all sort of have a particular order and structure in which you can connect them. And imagine, especially in one of these large enterprise programs, you can end up with a huge, thousands of nodes in this that all sort of need to fit together. So I'm going to make a little sharp left turn here. So to translate a lot of these ideas into Forth, the most direct and obvious way to do this is to apply an object-oriented Forth of some sort. And so to do that, of course, this is one of the great strengths, great challenges of Forth. It's very easy in Forth to do. For a one-off talk, a thing that in another language would be a complicated and deeply involved project, adding object orientation to the language. And so there have been many efforts to add OO to Forth, and unfortunately they don't hold a lot in common because everybody comes at it from a slightly different angle, has a different philosophy of how to add it. And so where, say, with C, between Objective-C and C++, you have essentially two major attempts to make it object-oriented. With Forth, Brad Rodriguez did a sort of a survey in 1996 already and found 17 different systems. And the first one I'd ever encountered was actually this book from Dick Fontaine. It was the only book on Forth I could find at the time in the Caltech library. So, but it was an interesting book nonetheless. The swoop system that the SwiftX folks put out is actually a pretty nice one, and I find it sort of nicer than some of the others and inspiring. This is what it looks like. It kind of mimics C++ a little bit, and it uses namespacing and vocabularies to let you sort of have methods and variables and use colon definitions that are bound to a class. But unfortunately, I've had challenges getting the portable version of it to work, and B, I'm going to be doing some things with the innards of the system, so I'm going to make my own. So I've thrust out into the world yet another one of these systems. I call it UFTA, object-oriented for something. Anyways, in UFTA, every object has a cell at the front of it that's a pointer to what's called a vtable in at least C++ parlance, which is just a table of all of the execution tokens of how you would respond to different types of methods. And then classes are themselves an object that has a vtable. And a big simplifying assumption I'm going to make is that I'll assume that all the vtables are the same size. And the nice thing that this allows you to do is it means that every method could be applied potentially to every object, which allows you to do things like duck typing. And it also simplifies things like you don't need to worry about whether or not when you invoke a dynamic method on an object that it's in the same part of the inheritance hierarchy. Methods in the system just become words that invoke a particular vtable offset. So if you have a print method, it will always, at the point when that method is initialized, some index will be picked for it. So it'll always be, say, slot number 3. And then it will invoke that element of the vtable of any given kind of object, regardless of what type it is. Similar to, actually slightly different from SwiftX, there's no way to reach in and access data fields other than at definition time. So that kind of provides private data fields, but then public methods. So all the methods on an object are public and dynamic. So none of the distinction of, like, say, non-virtual method. Everything's virtual in the C++ sense if you're connecting it to that. I support only single inheritance, and because of as I mentioned, the shared vtable structure that every object has, no interfaces are required. So just to make that a little bit more visual, if you've got an object, it is a pointer to a chunk of memory that has as its first element the type. The type is a pointer to a vtable, and then it has all the rest of the data in the object. And a method is then just a word that you invoke with an object sitting on the stack that goes to a particular slot in the vtable of the object on the stack and executes the execution token of that word. And so definitions look like this. Here I'm defining a 2D point, and I use the convention that methods start with a dot. This makes them look a little bit like C++ methods, but it also works cleanly with another design choice I've made, which is that every method, regardless of what vocabulary you define it in, always gets stuck up in the fourth vocabulary, because these are effectively global to the whole program. And so it's useful to have them have a unique prefix. And so here you can construct a point, you can reference values within the point and do things with them. I've got a second syntax. I find I sometimes want to use values. And you're allowed to use values where instead of doing load and store to them, you do to you can just use them by name and do to. Unlike a regular value where you would set an initial value, here the assumption is the constructor always has to initialize things. If you don't initialize things, they're zero initialized by default. So the system zeroes out any memory that it allocates. If you wanted to inherit from one of these, you can use extends, which will go and execute that word and get get the class for that you want to extend. what that operation actually does is it copies the vtable as a starting point, and then the elements within the data elements are tacked in the bottom of the object, and then you can use super to call methods from the parent. So the way you actually instantiate an object, you reference its class. Because the classes are themselves objects, you call .new on them. The parameters to the constructor get pulled off the stack, and then you can stash that away somewhere and then call methods on it. Just to sort of frame the structure again in memory, if you had an instance of a point P, you'd have the first cell of that point is going to be a reference to the vtable, or the address of the vtable, and then you have the x, y, and z for the point. This is a 3D point. It points to a vtable inside of point 3, which is itself an object. The class point 3 is an object, and its type is in turn this sort of mother of all classes, class. And it also has elements to track whether a particular class has a parent, and then the size of the class, so that there's the size of the elements of that class, so that you know how to allocate them. And then you can follow up to the parent, and you'll notice here that both point 3 and point 2 are members of class. Class is sort of an Ouroboros because it is itself a its type is its own vtable, and so it sort of bootstraps things that way. Whoops. Let's see. So you can do dependency injection in the most sort of direct way with this. You could define bar and baz as we did before, and in the constructor you can store into your values and then do something with it in other methods. And just as before in Java, you could do bar baz on the stack and then call new on foo and construct an object. I'll dive briefly into the implementation, but try not to linger there too long. As I mentioned with fixed method count, there's a way to override this. If you're using it as a library, it defaults to 100. And then I use a global variable for this pointer. But although it's global, the system is reentrant as long as it's not multi-threaded, because every time you enter a method, this value gets stashed in the return stack, the new this value gets loaded, and then it gets restored as you return back out. I keep most things for the system stashed away in a vocabulary called classing, and then, as I mentioned, methods are always put in the fourth vocabulary. So as I said here, there's a constant oofta max methods that lets you set how many methods you want to have. Everything's in a vocabulary, and then there's this variable, and then these are the sort of the largest and most complicated words in the whole system. Basically, what I'm doing here is keeping a count of how many methods I've seen so far, and then I have a new method that creates a new method. This is an implementation detail, but it takes the next parse token and creates a word that does the whole dance of stashing away this pointer. I store for a purpose you'll see later. The last method invoked is always tracked, and then invoking a method through the vtable and then restoring to this pointer. And then this in turn is wrapped with this method word, which will try to create a new method, but will reuse the old definition of that method if it already exists. And this saves me the trouble of having to worry about who is the first word that used a particular method name. So whatever the first time that you encounter a method declaration, that will be the point in time when it gets assigned an index. And then some other convenience words wrapped around this, a way to get the index number for a given method name, a way to just force a method to be allocated. Occasionally you want to reference a method before anybody has defined a method of that sort. And then I go ahead and make construct method 0, although I don't think I actually depend on this anywhere. And then I've got this mbang word that lets you, for a particular object, reach into its vtable and override what a particular method does. And then one other sort of flourish, let's say, that the system has is that mimicking Smalltalk, there's a notion of a fallback. So if you invoke a method in the vtable and it is undefined, what I do is I intercept that with a sort of a default handler, this undefined word, that will redirect that method invocation to a method called fallback. So if you invoke a method on an object that isn't defined for some reason, rather than directly fail, it will call fallback. And then fallback, I have an error handler that by default just prints an error, but this allows the possibility of a word that acts as a proxy. So it will intercept unknown methods that are called on it, and then can do something with them programmatically. This lets me then build up that class, the mother, sort of the root class, that and it references its own vtable and then starts with a blank vtable. I do a little bit of setup then to inject into class the very first method in the system that actually has an implementation called set method, and this at that point allows me to then sort of every time I'm using objects from there on, I'm always using the object, invoking methods on it, and no longer have to sort of reach into their implementation details. I have a bunch of then words that are defined for inside that vocabulary scope. I have an alternate version of create that stores away in a temporary word the size of the word, so the size of the class that you're building up, and then at runtime we'll go and fish out a value at that offset. Similar idea for variable. Similar idea also for values in 2 with a little bit more complexity to let you make that syntax work. And then super actually starts using method invocation to go and examine when you invoke it on a method, it will actually use class, get the class of an object, find its parent, go get its vtable, and then execute something out of that vtable. So it's gradually starting to use the object system more. Colon reserves a number for it for the index of a new method, uses no name to define that method, creates an execution token for it, and then uses set method to store it into the vtable. And so, and then the methods the words for defining classes are then fairly easily built up. You're able to set the current this to the class you're defining, and then accumulate words into it. And so at this point, I've got extends and sort of all of the special words within the system, and then I've got this word extend that lets you, after a class has been defined, go back and add additional methods into it. And so that at this point lets me go and add a whole slew of words into class, or so a whole slew of methods into class that give you things like the ability to go examine the vtable, allocate objects, find out the names of objects, construct a new object by allocating space for it, blanking out its vtable, using the vtable from the parent class, and then do things like inheritance, copying over those vtables. So all of that gets sort of gradually more So anyways, that gives you a sense of the system. That's literally, I think almost all the code in the whole system just got flashed on the screen. It's not a very big file. I think it's like 100 lines. So let's swing back to the problem of dependency injection. So all this hooking up of things manually, as we saw with foo and bar and baz, can get tedious very fast. And even if you imagine, setting that up globally somewhere, it's going to be really unscalable. Every time you've got to figure out sort of how you're gonna cope with that, all of those pieces to plug together. And so the question is, of course, can we make it automatic and declarative? And this is the idea that sort of transpired in the Java community, because Java's on top of everything else super verbose. And so they have what are called dependency injection frameworks. And there's a sort of lineage of these where they've gotten progressively better, for some definition of better. But the granddaddy of these is one called Spring. And Spring actually dates back to a thing called Java Beans. And it has started down this path with the idea of specifying the dependencies in a blob of XML, which is super ugly, and is the config doesn't live with the code, and it's XML. And then what it does is at runtime, it loads this XML and then figures out, you tell it about all your objects, you give it a blob of XML, and then it assembles your, say, server or something at start time. And so you'd end up with something like this for the coffee maker, where you specify a bunch of beans for each of the different elements in the system, and you describe their dependencies, and then it will figure out the appropriate ordering to initialize them and glue them all together. This existed for a time, and then a feature got added to Java that sort of kicked off a little kind of mini revolution in these type of systems, a thing called Java annotations. And so the idea is that it's a tag that you can add on almost every symbol inside of a Java program. They typically start with an @ sign, where it's a sort of a syntax-aware extension to the language, and it lets you do things like compile time code generation that makes reference to some part of the code. And it's, in some sense, it's actually fascinating to look at from the lens of Forth, because it's a lot of complexity to do a thing that we basically do in Forth with immediate words, the ability to sort of extend the syntax of the language. So it looks like this. You can specify with @interface that something is an annotation, and then you can attach that annotation to various places in the code. So you might annotate a method and say it's got some particular attribute. And then you can attach data to these attributes. You can, I can't spell Rumpelstiltskin. You can attach numbers and strings, and even lists and complicated objects. And then you can specify a bunch of very complicated policy constraints on it to say things like this annotation should be kept around at runtime and can only be attached to, say, methods. And so this lets you build up a set of tags that can exist at compile time or at runtime or both, that let you sort of add extra stuff into the program. So it's a very roundabout way of getting sort of that immediate word flexibility. And a series of systems gradually use this to build a cleaner and simpler dependency injection framework. So basically, they went through the process of saying, well, initially, let's just use these annotations. We'll use annotations to specify how you would do dependency injection, and then sort of do all the things that was happening from the XML at runtime. And then gradually, more and more of the system pivoted to doing this at compile time, so you didn't have to pay for all of the cost of scanning through these objects and doing reflection to examine them. And so you end up eventually with Dagger 2, where you have something like this, where you can have your coffee maker class, and you can specify just this inject annotation, and then that indicates that you want the logger and the heat pump and the heater and the pump to get pulled in as needed. And so what this does is that now when you want one of these coffee makers, you just sort of say, well, here's the stuff I need, and you don't specify where you get it from or how it's initialized. So you sort of, for all intents and purposes, can treat it like these are objects that you know what you want. You want some sort of a pump, and you don't have to think about any of the details beyond the fact that you want to pump. Bunch of terminology in this domain. It's actually, I found it hard to wrap my head around it, but there's a sort of crudely add inject refers typically, but not universally, unfortunately, to places where you want to inject an object of a certain sort, and then provide is kind of the counterpoint to that. If you want to provide an object that accomplishes something, you use provides. And then these, you have what's called a module, which is not a module in the normal sense, but is a special class that contains a bunch of things that are provided, and then you have components which are built out of multiple modules. And this is the point where you can say, I want to plug together a whole bunch of these Lego blocks, and actually rather than plug them together explicitly, they will sort of self-assemble. And then another key tag is that you can use singleton to refer to the fact that you maybe want only one logger to exist in the system. So I've mirrored this in a dependency injection tool called Poke. I build on top of UFTA. I simplify some of these concepts that are in the frameworks. This is more of a library and less of a framework, I would say. And I use strings to describe the binding. So there's a sort of a string name. When I want to pump, that's not, in Java, that's a particular interface. But for Poke, that's just a string. I want a thing called a pump. And then unlike Java, where there's a bunch of explicit, sort of implicit injection, I've just had you use inject explicitly. And then providing, I do as a method. So a module that wants to provide something just implements provides for whatever that name is. And then I have rather than using an annotation or an annotation-like thing for components, I just have a particular component class that you can inherit from and then call some methods on. And sort of to see where this fits in, unlike some of the more fancy newer frameworks that do compile time injection, I'm doing essentially runtime injection, although some of it is being decided. It's somewhere in between, a mixture. So here's that coffee maker problem. It's a bit of a wind up for this, but this is what it looks like in this system. You, in the constructor, merely need to say, I want a coffee logger, I want a heater, I want a pump. And then you're provided with those things. And then you can just immediately say, well, I want to turn on the heater, do the pumping, log something to the logger about the coffee is there, and then turn off the heater. And so I can sort of have this style of programming where I just sort of conjure up the things that I need without concern for how they're obtained, use them as I want to use them. And then the only sort of embellishment is I need to specify that in this separate class, this coffee maker module, that this is the recipe for how you make a coffee maker.
Somewhere.
And then the same thing with the logger. I can describe how to do a logger in the abstract and then provide it. And I can even specify that I want this to be a singleton. I want only a single coffee logger in the system. And then I can, again, the same thing with the electric heater. I can say, well, here's, for this, I need a logger for the thing, and then I'll keep track of my heating state and can toggle on and off my heater, and I have a method to find out if the heater is on. And then I specify that in this heater module means that this is the way that provide a heater in this system. And the same thing with the thermosiphon. I need a coffee logger, I need a heater, and so you're sort of stating your dependencies, but not needing to be explicit about how they're initialized. And then this is the sort of the magic part where it becomes Lego block-like, or Lego block isn't quite the right analogy, but basically in your component, and I think this is why these kinds of systems appeal to large enterprise programmers. You have your component, and then you just, I want a heater, I want a pump, I want a logger, I want a coffee module, smoosh that all together and conjure up the system and figure out how to hook it up. And so You can build up very complex systems where you can think about individual pieces this way, and then you can run them and use them. I'm mindful of the time, and so we'll probably skip over some slides about the detail of the implementation. But broadly, the idea here is that I have a global to keep track of the current provider. I use immediate word magic to enforce if you specify that there's a singleton, there's only one of something. And then I use that fallback handler mechanism to allow each provider module to get routed to its children in turn. So if you have that way I can have a component that actually knows how to provide sort of everything. But I do keep track of how many providers exist for each thing, and that actually allows it to do error detection. So if, for example, in the system you have multiple different loggers, it will raise an error and say, wait a minute, you can only have one logger. Or if your pump maybe has a requirement that's not met, it will scream about that. In the implementation, I ended up needing an array class, which is easy to define in UFTA. This is just a sizable array. I was able to create inject with a fairly small number of lines of code to go looking for the right provider, and then singleton lets me actually within the current module object allocate a slot, and that way if you have a type of object that you only want to will have one of per component, this is a way to do it. And then a component is just a regular class that uses these fallbacks to then go through each of the different modules that have been included into that module and see if they can provide what's needed to instantiate a particular dependency. So anyways, that was a lot of complexity, a lot for Forth. And it's a lot of complexity even for Java, honestly. Like I have, part of why I thought to give this presentation and been thinking about something like this for a while is that even when I've seen this in the Java domain, like I really struggle with whether this much complexity adds value. I think some of the complexity versus sort of what you might typically do in Forth comes from the fact that Forth sort of thrives on singletons. What's called a variable in Forth is really a global variable. And I think that there's a bias in Forth towards the simplicity of assuming that you want one of something unless you have a particular reason to build an object stack or really go to a little more effort to pass it around. Whereas I think a lot of the complexity in these kinds of systems stems from the problem of wanting to have multiple of something and have flexibility to do that, but then potentially wanting to tag a bunch of objects as singletons. And in fact, I think one of the reasons I often think of Forth in the context of these systems, even in Java, is that you'll see folks use them and then effectively mark almost everything for large chunks of the code as a singleton, essentially making it almost like a global variable, which is sort of weird. But as I did this exercise of translating the coffee maker sort of pedantically, it occurred to me that Forth has a better mechanism to do this. And there's a more Forthy way to do the coffee maker, which I'll now show you. It's defer is. And defer is actually really, I think, captures the essence of what this pattern has in a much more Forthy way. It's really, instead of, in Forth, we don't build up whole class hierarchies typically. We focus on individual words. And so here's exactly the same thing, but I suspect it will be clearer and easier to understand. I want to know how to brew coffee. Well, I'm going to need a way to log. I'm going to need to turn my heater on and off. I'm going to need to pump, and I can conjure these up with the word defer, and then I can implement brew on top of them. And then I can, have my console logger, and I can just decide that that's how I'm going to log. And similarly, I can have my thermosiphon, and I can reference these prior deferred words to know how to determine if things are hot. And I can say that the thermosiphon is my pump. And the same thing with the electric heater. I can specify that it's the the electric on and off is the way that you do the heater on and off, and checking the status of its switch is how you check if things are hot. And then I go and brew, and it accomplishes the same thing. I'm defining a set of things, being loose about what the relationship is between them, gluing them together locally where appropriate, and then getting the output that I want. And so that's it. Here's the code. Are there any questions?
That was a great talk, Brad.
I have a question.
Well, yeah.
What if you want your objects to be somewhere other than in the main dictionary? For instance,
I don't know if you heard him, but John was talking, Travis. So let John finish.
Sorry, I heard a question there, and then what? Shall I answer that? I can answer that one pretty. So the .new word currently will dynamically allocate a word. It allocates it out of dictionary space, but there is an affordance to override the allocate method, and that could be replaced by allocation from a dynamic heap. But I decided that it was, for my purposes at least, dictionary allocation, dictionary or heap space allocation was fine. But yeah, there's an affordance in there to override that default. And probably if you were going to use this in any serious way, that would be a requirement that you would want to do that. I've also been a little bit fast and loose, if you didn't happen to notice, with the freeing of memory, which in Java, of course, they're able to lean on a garbage collector. Here, you would need to. Here, you're gobbling up heap as you go. So yeah. But unlike, say, a system like SwiftX, where you define a word, if you reference a class and it's implicitly given a name on the heap, here you're getting the address of the object. It's getting allocated out of the dictionary space, but it's a reference to it is sitting there. So you're passing around references. And I think, did John had a comment or a question?
More of a comment. One of the things I like about this is you literally have runtime. Well, how can I say it? You can create new objects at runtime, okay, and throw in all the necessary methods to do this object, which I really find very good. Now, implementing this, like say you really want to make a real coffee maker, so I'm thinking maybe like a Raspberry Pi or some other embedded chip that has necessary outputs, so that you can go out and control a coffee maker. That's one of the things that I really liked about this thing that you came up with.
So the coffee maker example itself is actually the sort of synthetic example that's actually gets used in the Java community, and I suspect it's probably because Java and coffee, and so folks will come up with it. But you're right, it's sort of a very synthetic. It's both sort of synthetic, but it's cute because it's sort of just real enough, and I think that's kind of why it sticks around as an example. Is it sort of at least has the shape of a more complex problem without being so complicated that you're spending too much time explaining the problem. But yeah, it would be fascinating to see an actual coffee maker done in this style.
Brad?
Yes,
yeah, Brad. I got to say, in many ways, this can map into, or Cozy sort of at a simpler level. But I mean, the object in Cozy, all objects are just lists of lists, and the header is just the type and the count, and the so far as I know, Forth is unique in having the quote, go and instead of executing a word, go and return its address. And thus it can be handed as a parameter to any other function and so forth. But those two aspects, I mean, one of the things actually in terms of having types, well, I've got to go and sort of, oh, your thing is so complicated with all these methods. I mean, essentially, it's just, you got the most complicated type in Cozy is a dictionary. And all of this structure is very much inherited from Arthur Whitney's design of K and transparency. But a dictionary is just a list of two lists. The first is the names and the second are the values. And when you have that, to go and make your little arrays and so forth, I mean, you know, that's just...
So I think I can address that and actually a question in the chat at the same time. So I think that it's my understanding is some of the approaches in both Cozy and sort of APL like things, it's similar to Lisp. It's this idea of do you make the most fundamental types, lists and things of that sort, and then build higher level concepts on those, or do you,
Arthur described K as being lists, but not just binary lists and item lists. And so essentially you have a vocabulary built on n item lists. And if you define your own type, a vocabulary for your own type, then all of the vocabulary for taking and dropping and indexing and so forth, which is all inherited from APL, goes and applies to whatever that type is that you've defined a fundamental type for. And the most fundamental thing, again, is lists of lists, arrays, that can be, and they can be arrays of dictionaries, the arrays of names and associated values.
So I actually don't know how much OO style concepts are sort of how those have been mapped into the APL and related communities. I know in the Lisp community, there's a sort of they have a similar problem to Forth. Like there are a few competing systems for how to do object systems. And one of the problems with having lower level primitives and then building up an OO system on top of it is now you have choices about, what kind of dispatch do you do and all these things.
Again, in APLs, they generally call it a namespace, but fundamentally, again, it's a sub list of names and values. And the values, of course, can be entire lists and in a sense, the fundamental data structure, I often think of it, rather, it's not just a tree, it's a bush. And the vocabulary is such that it goes and applies, to corresponding leaves of those bushes and so forth. And then that's yeah. So anyway, yeah, we obviously need to talk about the future of language, get offline and talk about the future of language, because this is very much about it.
I saw some questions in the chat about garbage collected forth. So if you go back some of past Fig Talks, I've done little garbage collectors. Typically, the challenge you get into is that you end up needing to use techniques like a conservative garbage collector, where you say, because you can't account for everything in the Forth system, you have to assume that if something looks like a reference to a piece of memory that it is. And there's a whole sort of literature around that. You can also sort of sidestep the question by making limiting assumptions, like you assume that objects will only ever exist on the stack or in certain ranges of the heap, things like that. So it's possible to do imperfecly. This is answering the question in the chat, but I've never seen sort of something super satisfying in terms of a garbage collector.
Brad, this again is something that actually I borrowed after having, the header on any Cozy object, like I've said, is a 3-cell header. It's type, it's count, and the third one is reference count. and all objects essentially do their own reference counting. Right now, when the count returns to 0, then it just goes and frees it. But I'm just using the op system freeing. Arthur uses a 2 to the n length slot inventory. So his entire thing is just either removing or adding, finding the slot. Well, it's essentially, again, a database sort of a thing, but he never moves anything. The conversation, he made a comment. This was at a meeting at Union Bank of Switzerland, I believe. But he made this comment that he never moves anything, in a sense that there's no, he doesn't garbage collect, he just goes.
We could probably talk about garbage collectors for a while. I think, one of the challenges, I guess, with reference counting is you need to make some assumptions about what you're trying to build. But yes, it's an interesting area. I want to cover some of the questions in the chat. Somebody asked if I've seen a forth with interfaces. I have not. As I mentioned with UFTA here, I've because you've got a shared layout for all of the V tables, you effectively can do duck typing, which is not the same, but it sort of sidesteps that. I suspect that some of the OO forths that are out there, you could kind of use a style like the way people will use the way people will do interfaces in C++ is they'll use inheritance of an abstract class and sort of use by convention the same pattern. So I would imagine that you could do something similar. My guess is it's just that a lot of the biggest activity in OO forths probably predates Java. So that particular pattern of giving a name to the idea of a pure abstract base is less common. So, and I think if that was a question in the chat, yeah, you can allocate it in the dictionary, or you can override and point to the heap. Although I don't have any code by default that does that, so you'd have to create a class and then override its allocator to specify that you wanted it to be allocated in a dynamic heap. So.
Brad, let me ask you if you want to expand on any of this, that you break it off into another talk for next month.
Will do.
Because it's about time we moved along. If you can unshare your screen, and Don, you're on. Introduce yourself and on with the show.
I love your talk, Brad. We'll have to talk about that when we get further down the road. Okay, so
I like the part where he said the obvious simple solution to this is
deferred. Yeah. When you started talking about it, I went deferred words. Yeah. So
at the very said this, and it just I somehow found that hilarious.
Yeah, the object oriented, I haven't run across a need for that functionality yet. I definitely see it like in Windows, because Windows, is an object, and then it does all this, you want to encapsulate it and all that stuff. Anyway, I'm going to talk about the Core 1 project, where we're at today, and where we're going to go in the future. So I put together a presentation here. Let's see.